Let us focus on the search for superheavy elements in nature. I would like to show you the calculations that brought us to the experimental point where we are now. Cold fusion was here. We moved up 5 orders of magnitude in neutron-rich nuclei. We are following the trend that was theoretically calculated. Of course, we did not reach the shell of element 184, which is required for upward movement. For this, it is necessary to obtain more neutron-rich nuclei. The alpha decay periods are written here. I must point out that spontaneous fission does not interfere with upward movement, because the growth of spontaneous fission, along with an increase in the number of neutrons, or as it approaches the shell, is much stronger here than for alpha decay. Another interference becomes clear as we look at the graph. Indeed, the age of the Earth is shown here, and here is the sensitivity which could be achieved in the search for superheavy elements in natural samples. If this sensitivity is not high enough, one could search for superheavy elements in cosmic rays, since the age of cosmic rays is less than 5.5 billion years. This leads to an argument about whether there is one generation of cosmic rays or several generations. There are, of course, young rays, and then there are older rays. But nevertheless, on average, this would allow us to move down to 10 to the power of 7 years, or 10 million years, if only these calculations were not ruined by beta decay. Beta decay makes it impossible to obtain the heaviest nucleus. So we need to move away from 184 neutrons towards a smaller number of neutrons. We are losing a lot of time somewhere in this region. Although I will say once again that these calculations have a large margin of error. Whenever we need to look for something in nature, we have to keep in mind that, although it may be possible, we also have to understand that the probability is very small. But what are we looking for? Remember, we looked at this incredible depiction of the formation of the universe. And we said that at the time of 10 to the power of minus 35 seconds, the Planck era ended. From that moment in time, up to this moment in time, down to the last microsecond, quarks and gluons passed into protons and neutrons, and then neutrinos moved away from this structure. After 180 seconds, light elements began to form. Then almost no change took place until the system cooled down enough, which took about 300 to 400,000 years, at which point electrons began to land in the orbits around the nuclei, and the temperature was about 300 Kelvin. After that, the situation hardly changed for 1 billion years, and then stars began to form. Now, we must understand a little more about how the stars were formed in order to understand how heavy elements were formed.